Hi, Year 13s. We're going to look at finding stationary points for implicitly defined curves. Okay, so remind yourself, how do you find stationary points on the curve? Okay, that's always going to be where dy by dx is 0, where the gradient is 0. You could have a maximum, you could have a minimum, you could have a point of inflection, but it's always where the gradient at that point, which is on the curve, is 0. So we're going to take two approaches. The first way, you differentiate, then you straight away substitute in dy by dx is 0. You'll tidy that up and get an equation either just involving x in a number or y in a number, or x and y. Now that has to be true, but also the original equation has to be true because the point lies on the curve. So you solve these two equations simultaneously. The alternative method, you differentiate as straight away, and then this time you rearrange to make dy by dx the subject. And once you've got that, you know that dy by dx is quite often, for implicit equations, a fraction, and you know that has to equal 0. So that's the same as saying that the numerator has to equal 0. So that gives you your equation that has to be true for stationary points, and you solve that simultaneously with the original equation because the point lies on the original curve. So let's have a look at a couple of examples. We'll do each method. So for the first equation, we have to find the coordinates of the turning points on this curve. All right. So we differentiate travelling along the equation. So the first term will give us 3y squared dy by dx because it's in terms of y. And then the second one, we should have a few alarm bells ringing. We have got an x term and y term multiplied together, so we need to use the product rule. So we could use u is 3x and v is y squared. Oops. If we differentiate those, we get 3 and we get 2y dy by dx. Now the product rule is going to give us v du by dx plus u dv by dx. So if we tidy that, we'll get 6xy dy by dx. Okay, right, and now we can look at the next term. So we get minus 3x squared equals, and differentiate 27, you get 0. So for this method, we are straight away going to substitute in dy by dx is 0. So we've got 0 and then a 0 here. So in between, we've got plus 3y squared minus 3x squared is 0. So that would give us y squared is x squared. Or we could write that as y is plus or minus x. Right, this has to be true, but also the original equation has to be true. So we're going to substitute in, let's do y is positive x first. So y is equal to x. So you substitute that in. So y cubed will be the same as x cubed plus 3x times y squared. So that's going to be x times x squared. So 3x squared. And then minus x cubed and is equal to 27. So we've just substituted in. Every time we see a y, we put a positive x. So altogether, that gives us 3x cubed is 27. And then that is x cubed is 9. So x is rather awkwardly the cube root of 9. And we know that y is equal to x. So one of the stationary points is going to be the cube root of 9. The cube root of 9. Okay, let's look at the one we haven't tried. So we haven't tried using y is negative x. So if we substitute that into the original equation, wherever we see a y, putting minus x. So y cubed is the same as minus x cubed plus, and then we've got 3x times, that would be x squared. So 3x cubed, and then minus another x cubed is equal to 27. So altogether, that just gives us a single x cubed is 27, which is much nicer. gives us x is 3, and we know y is minus x, so we are going to get 3 minus 3. So these are our two stationary points. Okay, let's have a look at the next method. So we're going to rearrange to get dy by dx first. The equation of the curve is given here. Find dy by dx in terms of x and y, and hence find the coordinates of the stationary points. So we need to differentiate this equation, and notice the very first term to differentiate is a product. So if I write u is x and v is y squared, when we differentiate those, we get 1 and we get 2y dy by dx. Okay, so let's use the product rule, v du by dx. So that is y squared plus u dv by dx. Okay, and then we've got equals, then we differentiate x squared, we get 2x, differentiate 1, we get 0. So that's it. So we need to rearrange this to make dy by dx the subject. So let's subtract the y squared, and then we need to divide by 2xy. Okay, now that's the first bit, and then we know that stationary points occur when this is 0. So we know that the numerator has to be 0 for that to happen. And so we get this relationship, y squared is 2x. Okay, now obviously it's going to be easier to not square root. So I'm going to have a half y squared is x. So wherever we see an x, we can replace it with half y squared. This has to be true for stationary points. And we know the point lies on the original curve. And so we substitute this into the original curve. So x times y squared, so x times 2x is going to be 2x squared, okay? And then equals x squared plus 1. All right, oh, well, this is nice. So if we subtract x squared from both sides, x squared is 1, so x is plus or minus 1. Right, now we know that we can substitute that in to get y squared. So that would give us that y squared is going to be 2 times x. So it's going to be plus or minus 2. However, if we want y to be a real value, then we need y just to be the positive one. Okay? And so y would be plus or minus the square root of 2. So our coordinates are going to be we want only the positive one. Okay, so we've got the x coordinate is 1 and the y coordinate is root 2. And we've got the x coordinate is 1 and the y coordinate is minus root 2. So just to clarify, so we've got x squared is 1, which solves to give x plus or minus 1. But if you substitute that in to our y squared is 2x, we get plus or minus 2. So we only want to keep the positive d there, so that means we only keep the positive 1 for the x. Okay, and that's the other method. So you can choose which method, unless, like in this question, you're directed to a particular version.